All right, so this is our nucleus of our atom, and we said that the electrons exist in these primary energy levels and concentric spheres around that nucleus. We looked at this yesterday, right? And so I'm going to put several, maybe I'll make 4 of these concentric spheres, which I'm representing with circles, actually. Okay. Huh? Wouldn't hurt. Since we're going to talk about how it is the spectrometry or spectrophotometry works. Okay. So let's say I have an electron that in what we call the ground state. That means it hasn't been energized by heat or by light. And so it's living down here on this first energy level, or in this first energy level. Okay? And I want to shine light at this electron. And it's white light. It's got every wavelength that we can see and some in the infrared, because that's what we're looking at with our UV-vis spectrometer. Right? Each electron has a certain note, at least, note is sound, but in light it's kind of the same thing. It's tuned to a certain note. All right? Now let me kind of try to relate the idea of sound and light. Both sound and light travel in waves. Sound travels through matter, light can travel through empty space. Both of them have waves. And just like sound has a certain note, you could say that light waves have a certain note. And the reason I like to tie those together is, we talked about yesterday how if you pluck a note on a piano string, the one next to it starts to vibrate at the same frequency. Did we talk about that yesterday here? Yeah. Okay. It's also true that if I pluck a certain note on the piano, or if I hit with the key a certain note, and then I take my thumb and stop those strings from ringing, I can hear other strings ringing. But it's only the ones that have overtones related to that, and that's why I was asking if you knew what overtones were. Okay, only those that have overtones related to that note. The same is true for electrons. Electrons just happen to be energetic particles. Okay. They're very much in the same category of particle as a photon. They're not exactly the same, but they have a lot of the same components or parts to them, okay? So if a photon, I'm going to represent a photon like this, an arrow with a kind of a wave thing on it, all right? This is a photon. This is my idea of a photon. Now, a photon can be thought of as a packet of waves, all right? So this is our image of a photon here. All right, so a photon hits this electron. Now it has to be the right photon. It has to have the right wavelength to make that electron absorb it. Just like the piano strings have to have the right note to make them start to vibrate. Okay. So if you have the right wavelength of sound hitting a piano string, the piano string starts to vibrate. It becomes energetic. Does that make sense? Or more energized. You don't know, but one will hit it that has the right wavelength. Okay? I mean, eventually you would know. We can look at our spectrometry graph we looked at a moment ago and figure out which wavelength works. Okay? Well, so let's just say that this photon just happens to be the right wavelength. Okay? Happens to have enough energy, that is to say, not energy, but intensity is what I mean to say. Has enough intensity, which corresponds to how high the wave is. Okay? So it has enough intensity for it to hit that electron and actually make it more energetic. Well, that electron then, according to the theory we call the quantum theory, that electron then gets promoted in energy. Okay, it may go to this level of energy, or it may go to this level of energy, or it may go to, this is all the same electron in different places because you can't have 3 electrons in the first energy level, okay? It may go to this level of energy when it gets hit by that photon. All right? So it all depends on the intensity of the wave that hits it, or if more than one photon hits it, okay? And that's because it's tuned to the same sound, the same note, like a piano string. It will absorb that energy and be promoted. promoted energy. Like the piano string starts to vibrate, this one becomes more energized and then gets more. It actually does vibrate more. Actually, we won't get into that too much. Okay. All right. Now it only stays here for a second. It doesn't stay long just for the tiniest fraction of a second. But if it comes back down here, it has to give away the energy it just absorbed. Okay. A photon is energy, has a right wavelength absorbed by the electron. It promotes. It drops down. It has to give away that energy. Well, what energy does it give away? The same wavelength of light as corresponds to this promotion. So it gives away a photon now of a different wavelength of light. Okay? Might not be the same wavelength here, but this is what it's absorbing. So when we looked at our spectrometry graph a moment ago, it's showing what photons are actually being absorbed. You were asking, how do we know what wavelength? We look at it on a graph like that. We look at through a spectrometer to figure it out. Okay? So what we're doing is we're absorbing this specific wavelength, or those other wavelengths that electron might have overtones to associate with, and it promotes. When it falls back, it gives away other energies of light, just like we gave away energy yesterday when we saw that green flame for boron in our Bunsen burner. That makes sense? All right? Either one of these, absorption or emission. So absorption means it's coming in and being held. Absorption means emission is being given away. Either one of those can be used to figure out what the chemical is that we're looking at. Both of those can be used to fingerprint that chemical. Both of them are types of spectrometry. Okay? Well, if I get promoted to the second energy level up here, and it falls back here, that's a different wavelength. That's a photon of a different wavelength. Okay? Now, once it falls to here and it falls back to where it started, well, that's the same wavelength that we had here. Okay? So that wavelength doesn't change from this one. Okay? If I go up here and I fall back to there, that's a new wavelength. That won't be the same as this one or this one. Okay, but it's a wavelength of light that's going to get given away. That's going to be given away by that electron. If I fall from there all the way back to the bottom, that's a different wavelength right there. Okay, that's a different photon that gets given away. If I fall to right here, that's a different wavelength. You can see what's happening here?
So how do they fall? Is it like different?
Because they only hold it for a second. Just like the piano string vibrates, but it eventually gives away that energy and goes dead. Right? The electron, in much the same way, gives it away a lot faster. But it gives it away. It gives away that energy to the surroundings, and it gives it away in the form of a photon.
Okay, and when it gives it away, you're trying to say it's not ever going to be the same? Like the both? I don't know how to explain it.
Well, let me put it this way. For this electron, the motions to this level is always the same photon wavelength. The motions to this level is always the same photon wavelength. The motions from here to here is always the same photon wavelength. So the different colors we see are as a result of all of these different possibilities. But they're very specific. And it's based on something called the quantum theory. And in the quantum theory that applies to electrons anyway, as it applies to electrons anyway, electrons can only go up those specific wavelengths, those specific levels. They can't go in between. They have to go exactly those wavelengths or those energy levels. Okay? So it's like steps on the stairs out here. I mean, you can't go half a step up there, can you? No. What happens if you try to go half a step up the stairs? You trip and fall down. And if you're wearing high heels, you break your head up or something. Okay? So I'm just kidding. Well, high heels are just not safe anyway, but some of the girls that wear high heels walking down those stairs, they scare me. God. Man. Huh? You need... Girls wearing those high heels up and down those stairs ought to be wearing helmets on their head, you know? Man. Anyway, okay. That's completely off the subject. Okay. Listen, there was a story last week. Was it last week? In the last couple of weeks, about a lady who was wearing high heels and tripped down the stairs and died? They thought at first she was murdered, but it turns out when the coroner started doing investigating, she just fell down this stairway that was a marble staircase and killed herself.
It's not funny, but it's funny.
Well,
It's just the idea that
it would just be better. So why do I not let you wear high heels in lab? I mean, there's water gets on the floor in labs, right? Okay, and you slip down. I don't want you to crack your head open on the lab table. All right. All right. So we're doing a lab tomorrow. Don't wear high heels, okay? All right. Let's get back to this. So all of this spectrometry stuff is based on this quantum theory, and the guy who first came up with this was a guy named Niels Bohr. And who did we name boron from that we used yesterday in the flame? Niels Bohr. Okay? Now his quantum theory idea was actually shown to be wrong in a lot of ways, but the basic idea behind the quantum theory is still true. Okay? Okay, just put that in your personal file. Jose. Got that? How that works? Kinda? Kinda, sorta?